Welcome back to the deep dive. Think about the last time you used some software, maybe paid a bill online or uploaded a picture. It probably felt pretty smooth, right?
Yeah.
Instantaneous even. But behind the scenes, there's this hidden world. The software's making tons of tiny decisions, running through steps again and again, super fast. So today, we're kind of peeling back the curtain on that. We're looking at the engine room, really, of programming, control structures. This is the stuff that turns basic commands into, well, smart automated systems.
That's a great way to put it, yeah. We've looked at sources that basically lay out the blueprint for how code works, how you can analyze it, make it better. Our mission today really is to go beyond just definitions. We want to give you the key insights, the core ideas about the three main pillars: loops, branches, and functions.
Right, so we're pulling out the specific keywords, the different types, the practical examples you actually need, so you can quickly grasp how programming logic is built and, importantly, why you choose one structure over another. It's about writing robust code, not just code that happens to work.
Okay, sounds good. Where should we start?
The foundation. Well, when you look at how any program runs, it really all comes down to controlling the flow, the order things happen in. And our sources pretty consistently break this down into three main types, these categories you find in almost any language: Python, C++, you name it. First up, you've got loops. That's your workhorse for repetition, doing things over and over efficiently. Second, branches. This is where the intelligence comes in, the decision-making part. And third, function or procedure calls. These are all about making code reusable and organized, scalable.
Okay, I see that flow. Start with repetition, the loops, then add decision-making with branches, and finally, organize it all with functions for scalability. Makes sense as a progression. So, if we start with loops, they're probably the first thing most people learning to code really latch onto, right? Because they solve that immediate problem. Typing the same instructions endlessly, they cut out the tedium.
And the errors that come with it. Human error.
Precisely. So within loops, you mainly need to focus on two core types that run based on conditions: the for loop and the while loop. Oh, and one keyword that's super important for controlling either of them is break.
The emergency stop.
Yeah, pretty much. Like if you're halfway through a massive loop, maybe 10,000 steps, and something critical happens, break just yanks the program right out of the loop instantly. Stops wasting time.
Okay, let's break down the for loop first then. This one feels predictable. You use this when you know exactly how many times you need to do something, right? Like do this 10 times or process every item in this specific list.
Right. You know the bounds before you start. The sources had that neat Python example, counting to 100 for I in range, 0, 100. That little line handles setting it up, counting each step, knowing when to stop. It's all contained.
Very predictable, which probably helps the computer optimize it too, I guess.
Definitely. That predictability is its strength. It's efficient. Now, contrast that with the while loop. Here, you're kind of trading that predictability for flexibility. A while loop runs a block of code as long as some condition stays true. That's the key part.
It doesn't know how many times it'll run, necessarily?
Yeah, nope. It just knows the rule for continuing. Like those analogies. Keep the heater on while the temperature is below 70, or keep asking for input while the user hasn't typed quit.
Condition-driven, not count-driven.
Exactly. But wait, we absolutely have to highlight the big warning sign here, the potential pitfall.
The infinite loop.
Yes. If your loop depends on a condition, like while count 1,000, you must make sure something inside the loop eventually makes that condition false.
Like adding the count plus one line. You have to remember that.
You have to. If you forget it, count never changes, the condition count 10,000 stays true forever, and boom, program frozen.
So while loops are great for unpredictable situations, but more responsibility on the programmer?
That's the trade-off, perfectly stated. Flexibility versus the risk or complexity of making sure it actually stops.
Okay, so we've got repetition covered with loops. But what happens when things get complicated? When the program needs to react differently based on, I don't know, user input or some changing data?
That's exactly where branches come in. This is the decision-making logic, using true-false conditions to pick which path the code should take.
And this usually involves three key parts working together: if, else, if, and else. So the if statement is the starting point, right? It's like asking a simple question: is this specific thing true?
Yeah. If the user is over 18, do this. If it's true, run the code block. If it's false, just skip it. Simple as that.
But what if you have multiple possibilities, not just one check?
Then you bring in the else if, or actually lots of languages nowadays like Python shorten it to elif. Same idea though.
Okay.
It lets you check another condition, but only if the first if was false. Then maybe another elif and another. It creates this chain of checks.
So it checks them in order.
In order. And crucially, once it finds a condition that's true, it runs that block and skips all the rest of the elifs and the else in that chain.
That makes sense. It's efficient. Doesn't waste time checking things it doesn't need to.
Exactly. Which leads us to the final piece, the real safety net. The else statement.
The catch-all.
The catch-all, the default, the if nothing else worked, do this instruction. If the main if is false and all the elif conditions are also false, the else block is guaranteed to run.
That feels important, like preventing crashes.
It is. It ensures the program always has some path to follow, even if none of the specific conditions you anticipated are met.
The driving age example from the sources really nailed this. Let's say the input age is like 25.
Okay.
So first check. If age equals 17, prints you're not allowed to drive. Is age 25 equal to 17?
Nope. False.
Right. So it skips that block, moves to the next check.
Oh.
Till if age equals 18, prints you're allowed to drive. Is 25 equal to 18?
Still false.
Okay, so the if was false, the elif was false. What happens now?
Now, because we ran out of specific checks, it falls through to the else doc block. And in that example, the else top prints, there was an error. Please try again.
Even though 25 isn't really an error, but the logic didn't have a specific instruction for 25.
Exactly. The else caught it. It prevented the program from just stopping dead because it didn't know what to do with the input 25. It provides a default behavior.
All right, so we can make code repeat things with loops and make decisions with branches. What's the next step in making code less messy and more manageable, especially as it gets bigger?
That brings us perfectly to the third pillar, functions and procedures. Think of these as creating reusable tools for your code toolbox.
Tools, okay.
Yeah, a function is basically a named block of code that does one specific job: calculate sales tax, validate user input, send an email.
And the idea is you write it once, then just call it whenever you need that job done.
Precisely. The value isn't just reusability, though that's huge. It's also about organization and clarity. If I see a line that says calculate tax amount, I instantly know what it's doing without needing to see the 10 or 20 lines of complex math inside that function.
It hides the complexity.
It encapsulates it, which is massive for working in teams or even just understanding your own coding 6 months later. It also helps manage something called scope-keeping variables and operations inside the function from accidentally messing up other parts of the program.
Okay, so these are like self-contained units. How do you actually use them? The sources mentioned 3 stages.
Right. 3 key steps. First, you have to define the function. You basically build the tool. In Python, you use the def keyword.
Like def my cool function.
Exactly. Def speak the truth. Print. Ron's Tech Hub is amazing. You've created the function, defined what steps it performs.
Okay, step 1, define. What's next?
Step 2 is often declaring arguments or parameters. Many functions need some input data to work with, right?
Like if you're multiplying numbers, you need the numbers.
Perfect example. You declare what inputs the function expects. So, def multiply integers, num1, num2. Here, num1 and num2 are the arguments, the placeholders for the data it needs.
Got it. Define the function, declare its inputs, and the third step must be actually using it.
Yep. Calling the function. This is where you tell the program, okay, run that tool now, and here's the specific data to use.
So like multiply integers 10, 51.
Exactly. You call the function by its name and provide the actual values, the arguments it needs for that specific run. You might call the same function many times with different arguments.
Okay, that seems straightforward. Define, declare inputs, call.
There is one more subtle but really important distinction the sources highlighted, the difference between a function and a procedure.
Oh, I thought they were kind of the same thing. Reusable blocks.
They are both reusable blocks, but there's a key difference in what they do for the code that calls them. A function is designed to compute something and then return a value back to the caller.
Like multiply integers would return the actual product, the number.
Exactly. It gives you a result you can then use. A procedure, on the other hand, performs some action, but it doesn't return a value back.
So like the speak the truth example, it just prints something?
Right. It does something, prints to the screen, but it doesn't hand a result back to the part of the code that called it. It might modify something globally or save a file, but there's no direct output value returned. Knowing this difference is actually pretty key for writing clean, predictable code. #outro.
Okay, so wrapping this all up, it feels like the big takeaway is that making sophisticated software isn't just about writing complicated code. It's more about using these fundamental building blocks.
Loops, branches, functions.
Right. Loops for the repetition, branches for the smart decisions and handling errors, and functions for keeping it all organized and reusable.
Yeah, they're the toolkit. They let you take simple instructions and build really complex, reliable systems.
So we've really dug into how code flows, how it makes choices, how it repeats tasks.
Exactly. We've mastered the control aspect, but think about what these structures are actually acting on. Every loop, every branch, every function call, it's all manipulating information. Data.
Hmm. Okay. Where are you going with this?
Well, we've figured out how to control the process, but what happens when the information itself gets huge and complex? When you're not dealing with 10 numbers, but say millions of user records or terabytes of sensor readings.
Ah, I see. So the control structures we talked about are powerful, but they need the data to be organized efficiently for them.
Precisely. How do you structure and store massive amounts of data so that these loops and branches can access it quickly and logically? What kinds of containers or arrangements do you need?
That sounds like a whole different kind of structure is needed, not for control, but for the data itself.
You've got it. That's the critical next step, moving from mastering control structures to understanding data structures. And that's where we'll likely head next time.